Hi everybody. Uh, this is in continuation of last week's session. If you remember, we are going to talk about the integral form of the momentum equation. Let's have a short review on what we said last week. We told that there are three physical principles, which are conservation of mass, the Newton's second law, and conservation of energy, and the resulting mathematical equations are corresponding the continuity equation, momentum equation, and energy equation. We discussed about the continuity equation last week, and this is the result, if you remember. For the conservation of mass, there's a relation, as you can see here, which is named Reynold transport theorem. In this equation, it is a relation between the rate of change of any arbitrary extensive property. Extensive means depending on mass of a system, and a variation of this property associated with the control volume, which is comprised of two parts: the variation within the control volume with respect to time, and the net rate of inlet and outlet from the control surfaces. If you remember, if we put mass instead of n, then eta will be 1, and this is the continuity equation in the integral form, or integral form of the continuity equation. Please refer to the recording of last week for more details. And today we want to discuss about the momentum equation. Writing the Reynold transport theorem again, this was the relation dn over dt, and the time rate of change, and the net rate of inlet and outlet through the control volume. To drive the control volume formulation of momentum equation, we set n equal to mv. P is m mass multiplied by v, and in this case eta, which is n divided by mass, will be v. So we put or substitute p or mv instead of n, and v instead of eta. In this case equation, with this substitution, we will have this equation, and as d of difference of mv over t is equal to the force on the system, so you may substitute force here instead of this item. The important point here is that the force actually on a control volume is comprised of two parts. The first is the surface forces, and the next one is body forces. So the force here is the summation of surface force and body force. This part is the same as I wrote here, and this is the same as you can see here. What is the surface force? Surface force is the are the forces which are acted on the surface of the control volume, like the shear force or pressure forces or normal forces or shear forces. And body force is the force which is in on the whole control volume. As an example, actually the most important example is the weight of the body, or gravity force. There are other types of body forces like electromagnetic, Coriolis, and these are other types of less common body forces. So generally in fluid mechanics, which we will study, body force is generally the weight, as you can see later here, and the other one is the stress. So this is the Reynold transport theorem, which is converted to the momentum equation in integral form. For cases when we have uniform flow at each inlet and exit, you can have then a summation here, or sigma instead of integral, because when v at a specific area is constant, then you can and can cancel in the integration, and difference of a, and actually all of these come out of the integral, and the integral of dA will be a. We discussed about the validity of this assumption last week. Please refer to the recording of last week. Equations A and B are our non-accelerating control volume form of Newton's second law. It states that the total force due to the surface and body forces acting on the control volume leads to a rate of change of momentum within the control volume, the volume integral, which is this part, the first part, and or a net rate at which momentum is leaving the control volume through the control surface. Actually, the leaving word here is the meaning is both entering and leaving. Here you can see that it's emphasized on net rate of leaving. So in actual case, you consider both entering momentum to the control volume through the control surface and that part of the momentum which exceeds the control volume from the control surface. So these are our equations. As I told before, the main or common body force which we will encounter is the gravity force, which is calculated in this way, and the main surface force which we will encounter is the pressure force acting on the control surface. And as this equation is a vector equation, in three-dimensional case you have actually three equations. The first in, for example, in the x, the second in the y, and the third in the z direction. Please note that in each case you should write the corresponding component of the velocity. For example, when you write the y direction of the momentum equation, you should put v, small v, instead of vector, which you can see here, or the same here. But there is an important here that you should consider, and that is this part. This part, which is the dot product between v and dA, you cannot put, for example, u instead of v here, because first you should do the math here, for example, for the dot product, and then you can put the appropriate value. So please note that for each direction we will put the corresponding component of velocity, for example in the x direction, which is u here and here instead of v, as you can see here. But for this one you should do the math, which is the dot product between v and dA. Okay, the same applies for the case when the inlet and outlet velocity are the same within the control surface. There are some examples in the book. You know what's the reference book for this part. Please refer to the previous recording. I'll show you again just within seconds. There are examples in the book. For example, this is one of the examples. There is a nozzle here where the water exits from the nozzle and hits to a plate. The question is, what is the force exerted on the plate? In this case, generally the procedure is, the first step is to draw a control volume, actually like a free body diagram, which you use in static course. And there is some discussion in this example 4 in the book, that what is the appropriate control volume. For example, is it better to take the control volume like this or this? And the answer is the right one. Please read this example and also example 4, 5 and 4, 6 in the book to know more about it. Okay, and the next session is governing equation in the differential form. In this and the previous week presentation we discussed about the integral formulation of the governing equations. As you can see here in the first slide, in this part we discussed about the governing equations, both the continuity and momentum, in their integral form. Now we want to discuss about the differential form of the governing equations, both continuity and momentum, in the next session. See you there in the next file. And this was the reference book which we use for this and the next part of the presentation. Thank you and take care.